All right, so this is the first part of the videos for week 2. We're covering chapter 2, and chapter 2 is largely devoted to the behavior of the sky, generally as viewed from an earthbound perspective. When you look up at the stars at night, throughout all of history, what stands out the most about the sky is that there are potentially thousands of stars that you can see if you have a completely dark area. And there are patterns that we recognize in the stars. And all throughout history, different civilizations have associated those patterns with things that are common to their culture. As you see in the example here on the slide, on the right-hand side, we have Orion, and that's a very famous constellation. It's very easily viewed from both the northern and southern hemispheres. The stars in Orion are quite bright, and so they stand out. And even in an area that's very populated, a lot of light pollution, sky is not so dark, it's pretty easy to make out the pattern that is Orion. People generally see the belt and the stars that make up what is generally seen as the body of a person. And that's something we hear a lot about for the stars in the sky. However, in professional astronomy, the constellations actually don't hold a lot of importance, even though historically constellations have been considered very important. And the reason why is for a lot of reasons. Constellations a lot of times are used by amateur astronomers for what's called star hopping, to help them do stargazing. For professional astronomers, we don't do that. Most of the equipment we have allows us to automatically point towards objects without the need to align with stars in the sky. So, and then also we are generally interested in really small patches of sky, things that are very, very dark and deep in space, and the constellations, don't really provide much help for those kind of things. There's another reason why constellations aren't considered very important, is because the patterns that we see are not scientific in any way. The patterns that we see, are really a function of a lot of things. Orion, for example, is generally seen as a person, and they're generally either holding a sword and shield, or maybe like a bow and arrow, and they're, retracting the bow. But if you see in the picture here, if you live in the southern hemisphere, that same pattern of stars looks upside down, because you are literally upside down with respect to those stars. And as far as I'm aware, I don't think any civilization from the southern hemisphere has viewed Orion as an upside down person. In fact, it's usually broken up into other smaller constellations. What's generally looked at as the bow has been seen as a canoe by at least one particular civilization. So because of that, we know that the patterns are not there because of some scientific reason. They're just there because by chance. And the patterns that we see are a function of a lot of things. They're a function of, where we are in the galaxy. If you go to a different location in the galaxy and you look at the same group of stars, you'll see a totally different pattern. The stars move, and so does the solar system. And so over time, the patterns will shift. And now over a person's lifetime, not too much, but over the course of maybe tens of thousands of years, that shift can be noticeable. So the patterns that we see now are just, because we happen to live at this particular time. And of course, the patterns that we make out are a matter of cultural perspective. A lot of the southern hemisphere patterns that have been created were created by European explorers traveling to the southern hemisphere the first time and bringing back star maps, and people made patterns of that. And so they had things like telescopes and other instruments and things like that they associated with those patterns. In fact, a really good way to think about this is, imagine that the constellations are like looking at a cloud in the sky. When you look at a cloud in the sky, you may look up at that cloud and say, well, that looks like a teddy bear, because maybe you like teddy bears and you see teddy bears and things. And but somebody standing next to you may see a completely different pattern because of it just looks totally different to them. And somebody who is in a totally different city and looks at that would see a different shape, because there's a different line of sight. And if you go back an hour later, the pattern's not going to be there. So that's sort of the reason why the constellations aren't incredibly important. to say a little bit more about that, there's something called a projection effect that occurs. The patterns that we see are the result of the direction we look. When we look out into space, we don't have a sense of depth. That's very easy to do. So as an example here, the Big Dipper, turns out that a couple of the stars in the Big Dipper are actually much farther away than the other stars. And so the pattern that we see is just when they all project out in two dimension, that's what they look like. But if you were to shift to a different location, say significantly outside of our solar system, and you look at that pattern, you look at it from a totally different angle, and you wouldn't see that same shape at all. So yeah, anyway, the patterns that we see are not really a function of anything scientific. They're just a function of, right place, right time, and what do you see. So as a result of that, the constellations don't hold a lot of importance. I mean, there are some things that the constellations are recognized and used for. Now, when we talk about patterns in the sky, we actually have a different term that we like to use for that. Instead of using constellation, we actually use the term asterism, and that is an unofficial grouping of stars. The Big Dipper is a good example of an asterism. The Big Dipper is actually not really a constellation, even in the traditional sense, because it's part of a larger constellation called Ursa Major, which is, a lot of cultures have viewed that as like a bear or something. And the Big Dipper is like the abdomen and like the tail or the backside of the bear. And the summer triangle on the right here is just something you see in the summertime. There's three bright stars that appear to make a triangle, and so these are all common asterisms. In fact, the word constellation today has actually a different meaning in professional astronomy. The term constellation actually refers to a region of sky, and that region of sky is loosely associated with the traditional grouping of stars. And there is a organization in astronomy called the IAU. It stands for the International Astronomical Union, and they are responsible for naming conventions and standards and all sorts of official things in astronomy. And a while ago, the IAU decided to split the sky up into 88 official regions, and this is what we call the constellations today. So when you look at the traditional grouping of stars that make up Pegasus, you're looking in the direction that has been defined as the region of Pegasus. They're used in like star names, and they're useful to refer to big chunks of the sky. But aside from that, the constellations don't have a lot of importance really in astronomy today. Properly we should be using the term asterism if you want to talk about patterns that you see in the sky. All right, so we want to start thinking about how the sky looks. We're going to start off with a more static view, not thinking about the motion of the sky quite yet. We're just going to be thinking about, what we can see just from being as a stationary observer. And in order to do that properly, you really have to know where you're located. And what you see in the slide here is something that you're probably familiar with, and that's the system of latitude and longitude. The system of latitude and longitude helps you identify a unique location on the sphere of the Earth. And knowing that location is really important for understanding what you can see in the sky. So just to go over that real briefly, latitude is an angle that starts from the equator, which is defined to be 0 degrees, and you can either be north or south of the equator. If you go all the way up to the poles, you're at 90 degrees. So it's an angle between 0 and 90 degrees, and that determines how far north or south you are on the Earth. There's a similar line, a group of lines called longitude, and the reference line is the prime meridian, which goes through a location in the United Kingdom, and that's called 0, and you can be some number of degrees west or east of that. And if you go all the way to the other side of the Earth, that would be 180 degrees. So you can be some number of degrees east or west of the prime meridian. Now, if you see at the bottom here, the latitude and longitude for Lancaster, California is 34.7 degrees north and 118 degrees west. And so you're going to want to make sure that you remember these numbers because when we talk about what we can see in the sky, it's really important to remember where the observer is located. Okay. So let me ask you a question about this. This is not something you may immediately know, but just try to get a sense of what this might be. The question here is, for the purposes of understanding the positions and motions of objects in the night sky, which of the following is or are important for an observer to know? So think about that for a moment. You may want to pause the video to think about this question. But the answer here is actually A. A lot of people generally say C for this, probably because I just went on talking about how you should know latitude and longitude. But it turns out latitude is the only thing that really matters. And the reason why this is because the Earth rotates in the direction of longitude. And so if there's areas of the sky that you can't see because of your longitude, you just need to wait until the Earth rotates far enough to see those areas of the sky. As an example, if we live in the southern part of the western United States. Well, if you go to the southern part of the eastern United States, the difference in time zones is about 3 hours, because it takes about 3 hours for that area of sky to rotate over to where we are. So if somebody lives in, say, let's say Atlanta in Georgia, and they look at their sky at 8 o'clock at night, and they see a certain number of stars, at that moment you're not going to see those stars. But if you wait until you're 8 o'clock, then the sky's going to move, and you'll see sort of the same things in the sky. So the longitude actually is not very important because of that. Latitude does matter, though. The Earth doesn't move in the direction of latitude. And so what that means is there can be certain areas of sky that are just not visible at all. If you in the southern hemisphere, at least for where we're located, there's a lot of objects that you can't see at all. I mentioned in the last video lecture the star Alpha Centauri. In Lancaster, California, you cannot see Alpha Centauri. It is so far to the south that due to the Earth's rotation, we never rotate into an area where we could view that star. Likewise, if you're in the southern hemisphere, there are areas of the northern sky that you just cannot see. So latitude ends up being the sole coordinate that really matters for looking at things in the sky. So you really need to remember Lancaster. It's rounded to 35 degrees. Okay. All right. Now, when we want to identify things in the sky, the way we talk about them is in terms of an angular size. And that simply means how large things appear. Which is a function of how large they actually are and how far away they are. To give you a sense of that, if you were to stick out your arm and hold your thumb up, the amount of sky that you would block with your thumb is about 2 degrees of sky. If you hold out your entire palm for a lot of people is around maybe 10 degrees of sky or so on. So we take, the horizon we call sort of 0 degrees, and as you go all the way up to the very highest point in the sky, it's 90 degrees. And so it gives you a sense of what those angular sizes are. Now, we talk about things in degrees a lot, but a lot of things that we view in the sky are very small. And so we have to talk about smaller divisions, and we don't use decimals for these angles. Actually, we use what are called arc minutes and arc seconds. An arc minute is a 60th of a degree. So if you imagine 1 degree, which a degree might be about maybe the width of your pinky at arm's length, and if you imagine that in 60ths, that would be 1 arc minute, and that actually happens to be the angular resolution of the human eye. If your vision is good, then the smallest detail you can see is around an arc minute. And then you can further subdivide arc minutes into what are called arc seconds. So 1 arc minute is 60 arc seconds. And to give you a sense of how small that is, if somebody were to stand 10 meters away from you, which 10 meters is around a little over 30 feet, and they hold up a single human hair, the thickness of that hair is about what an arc second is. And so it is an extremely small angle. It's not something that is observable with the naked eye, but in telescopes we can see details that are that small. So when we don't want to describe the distance between objects, or when we want to describe how big an object appears, we typically are going to be using degrees or arc minutes or arc seconds to do that. Okay, there actually is a formula that you can use to figure out what the angular size of an object is going to be. The formula is given at the bottom here. The name for that is the small angle formula. It has 3 parts to it. The upper left-hand side is the Greek letter theta, and that is the notation we use for angle. And the way that this equation is designed is that as automatically in arc seconds. That number at the bottom, 206.265, is a conversion factor, because normally this equation is given in terms of the unit of radians. But you can convert that to arc seconds by putting that number in there. On the right-hand side, there are two D's there. The D on the top is the linear diameter of the object, so how large the object actually is, and the large D on the bottom is how far away it is. So if you know how large an object actually is and you know how far away it is, you can use this equation to determine how large it would appear in the sky. So actually, we can do an example of this, and I'm going to work out an example here that you can see. And on your homework, you're going to have an example that's going to be extremely similar to this one. So we want to know how large the moon is, how large it appears to us. We know that the diameter of the moon is 3,470 kilometers. We know that the average distance to the moon is 384,000 kilometers. So if we're going to apply that to the small angle formula you see at the bottom here, we're going to have to arrange things a little bit. And we arrange some things a little bit. So the small d in the formula is the 3,470. The large D is the 384,000 kilometers. And then with that conversion factor, 206,265, we're going to multiply both sides of the equation by that, so it's moved to the other side, and so that allows us to solve for the angle theta. So putting all those numbers into your calculator, and you should do this as you watch this to make sure you're getting the same numbers that I'm getting, would give you the number 1,860 arc seconds. And that's a pretty big number for arc seconds, and so we want to try to figure out what that might be in a unit that's more manageable to work with. So I need to convert it into arc minutes, and then I'll convert it into degrees. Now, if you remember what I said earlier, a 1 arc minute is 60 arc seconds, so we can divide our number by 60 once. Then we want to get into degrees, and remember 1 degree is 60 arc minutes. So that means a full degree is 60 times 60 arc seconds. 60 times 60 is 3,600. So if you divide those two numbers there, 1,860 divided by 3,600, you end up with a number that's just over a half a degree. And that's how big the moon appears to us. So I remember I said about the pinky. A lot of people's pinkies are about a degree when you hold your pinky out at arm's length, so you can easily cover up the moon with your pinky. Yep. And on your homework, I'm going to ask you to do the exact same thing, but you're going to do it for the sun. I'm going to give you the diameter of the sun, and I'm going to give you the distance to the sun. And you have to go through this same calculation. In fact, it is completely identical to the example here. You simply need to replace the diameter and the distance with the numbers for the sun. And that's the exact same procedure that you use. And one of the things that you will see is that when you calculate that angular diameter, you will find that it is extremely similar to the moon. The moon and the sun have almost identical angular sizes. And this is going to be a very important point when we get into, I believe, the fourth chapter, and we talk about eclipses, because the fact that the moon and the sun are very, very similar in their size means eclipses become very interesting. Because sometimes the moon can cover up the sun completely, sometimes it can't, and so we have a kind of a variety of solar eclipses because of this reason. So we'll talk about that again when we get into chapter 4. All right, so now what we want to do is we want to start talking about how we look at the sky and how we, define what we see in the sky. We have a model that is used to explain the appearance and motion of things in the sky. And that model is called the celestial sphere. It's a model. It's meant to describe some behavior. It's not completely 100% accurate. It doesn't need to be. It just needs to describe what it's meant to do. The way the model works is we treat the Earth as a stationary object. We rotate the Earth so that the observer, no matter where they're located, is on top of the Earth. So that when you view the sky, you're viewing the sky from the perspective of you being on the top of the Earth. You don't want to think about viewing the sky as if your head is tilted to some angle or something like that. And then we let the sky move. Okay, so that's a fair thing to do in the model, because due to relative motion, it's very hard to tell the difference between Earth rotating, and that's why the sky moves, or the sky actually moving and the Earth being stationary. So that's why we can get away with this kind of model here. Now, in this system, we have a couple different ways that we talk about what we see in the sky. The first part of that is called the horizon system. The horizon is exactly what it sounds like. It's sort of the furthest you can see in any particular direction. The horizon divides the sky into a visible portion and a non-visible portion. And so it exactly splits the sky in half. There's a couple things on that horizon system. Most importantly is a point called the zenith. The zenith is the point that is directly above the observer's head. It doesn't matter where you're located on the Earth. Doesn't matter what your latitude is. The zenith is always the point directly above your head. There's a similar point that's not visible. It's called the nadir, and it's directly underneath you. That one, obviously, because you can't see it, is really not important for us at all. There is another system that is focused on the coordinates of the Earth, and that is called the celestial poles and the celestial equator. And what those are, I'll start with the poles. I'll just actually start with the North Celestial Pole. The North Celestial Pole is the projection of the Earth's rotational axis into the sky. So imagine this. Imagine you are actually standing at the North Pole. Now, when I say the North Pole, I'm not talking about magnetic north. That's different. I'm talking about 90 degrees north latitude. You're standing on exactly the Earth's axis of rotation. And if you do that, the North Celestial Pole would be directly above your head. It would be at zenith. So if you imagine there's a person there, and they have this enormous laser light that is so intense that when they shine up into the sky, no matter where you are on the Earth, you would see this light in the sky. And, obviously for the person at the North Pole, that point is directly above their head. But if you are further south from the North Pole, that's going to appear at an angle. And the farther you are from the North Pole, the further down in the sky it appears. So that is a latitude-dependent thing. And that is a very important point because that point helps us understand how stars rise and set. Because as the Earth rotates, all the stars basically do these giant circles about that point there. The celestial equator is the projection of the Earth's equator into the celestial sphere. And that goes exactly from east to west. And it's a line. It crosses the midpoint in the sky depending on your latitude. Okay, so, simply describing this stuff is not totally, sufficient to understand what's going on here. So I'm actually going to show you a program that illustrates this stuff very nicely. Okay, so the program that I'm going to show you here is called Stellarium. It's Stellar IUM. You can just Google that. It's a free program, so it's something you can get if you would like. What it is, it's sky simulation software. It allows you to view what the sky is going to look like at any location of the Earth and at any time. You can even go back 1,000 years and you can see what the sky looks like. A program like this is really good for illustrating some of the concepts related to the celestial sphere. So let me first sort of introduce you to the different lines and things we have here. The blue line that you see that goes right up from south is called the meridian. And that line splits the sky up into east and west. And it's where the terms AM and PM come from. AM being anti-meridian, that means the sun is before that line. And post-meridian is when the sun crosses the meridian and it's on the other side, and that refers to it being later in the day. The meridian is a line. It goes from south and all the way up and over and down to north. You can see the celestial equator here. The celestial equator comes right up through east, passes somewhere overhead, and goes down to west. So it's a line, and exactly where it crosses on the meridian is a function of latitude, which we will get into in a moment here. Okay. The North Celestial Pole is here, although it's not labeled here, but it's very easy to identify. What I'm going to do is I'm going to allow the sky to start to move. And what you will notice is when the sky starts to move, you can see when you look to the north that the stars are doing these circular motions. I'm going to hit it one more time to make it go a bit faster. And so now if you notice, there's a particular spot, and it's very close to this bright star right here. That bright star is what's called Polaris, and that is also called the North Star. And that star is about a degree away or so from the North Celestial Pole. And so for what we care about effectively is the North Celestial Pole. And North Celestial Pole is important for us because all the stars are doing circles about that point. And so identifying where that is very helpful. Now, on the southern hemisphere, you would have a South Celestial Pole. Unfortunately, there is no star that's very close to that area. So it's not easy to tell where that is by just looking. You kind of have to see motion or something for that. Now, I mentioned that these things are latitude dependent. And what I'm going to do here, I'm going to put up an additional grid that's called a altitude grid. So let me put that up here. And this altitude grid helps us identify how far up in the sky objects are. So the horizon is 0 degrees, and you'll notice where this point is located. This first line's 10, then 20, then 30, and this is kind of around the middle. It's about 35. And if you remember, our latitude is 35, and it turns out that that's how you are able to find where the North Celestial Pole is. It is above the northern horizon by an amount equal to your latitude. Okay, so let's look above us. That point directly above us, that's our zenith point. If I turn and look to the south, you see where that equator is. And if you look from zenith, if you go down, so zenith is up here. If you go down, we got 10 degrees here, 20 degrees here, 30 degrees, and that line is right in the middle between 30 and 40. It's at 35. And that's also a latitude dependent thing there. So where the celestial equator crosses the meridian is equal to your latitude. It's 35. So for Lancaster, it's 35 degrees south of zenith. So it's very easy to identify where these things are located if you know your latitude. I'm going to focus more today on the North Celestial Pole. A later lecture, we're going to talk more about the equator. The equator is helpful to us because it helps us identify where, typically the sun and the moon and the planets can be seen in the sky. But today, this lecture, at least this video, is going to be focused on the North Celestial Pole. All right, so let's actually go back to the slides here. And this is another great way to visualize what the celestial sphere can look like. This is a time exposure. I think it's about, based on what I see here, maybe about 4 hours of time or so. So we're looking towards the northern part of the sky. Somebody had a 4-hour exposure, and when you do that, it becomes very obvious to see where the North Celestial Pole is. It's the center of all these arcs here, and the Polaris is this little tiny bright arc right there. And the motion of this, so if you were to time how long it takes one of the stars seen in the picture here to complete a full 160 degree motion about the North Celestial Pole, you get the time that's up there at the top, 23 hours, 56 minutes, and 4 seconds. And that is what's called the sidereal day. It is the rotational period of the celestial sphere, which means it is the rotational period of the Earth. That's how long it takes the Earth to make one complete rotation. Now, the thing you're probably thinking about right now is, well, it's not 24, so what's the difference here? And to say it simply, the day, the clock, 24-hour clock, is not strictly based on Earth's rotation. Those are different things. And to understand that, I have a little diagram here that explains this. So the 24-hour day is what we call the solar day, whereas the 23 hours, 56 minutes, and 4 seconds is what we call the sidereal day. The term sidereal means with respect to background stars. And the reason why there's a difference is because we need to keep track of time based on how the sun behaves, not based on how the Earth actually moves. The sun's motion in the sky is a function of two things. It's mostly due to the fact that the Earth rotates, but there's also a small component that's based on the Earth's orbit. And so in the amount of time it takes to do a full rotation, the Earth has moved in its orbit. And so when we look in the exact same direction we did on the previous day, the sun is not in the exact same spot. There has to be a little bit of extra rotation due to our fact that we moved in our orbit to bring the sun back in the same position of the sky that it was before. And that takes about 4 extra minutes or so. And that's where we get the solar day from. So there's a difference between these things. The important number is 24. The sidereal day is like trivia. It's mostly meaningless unless you're taking this class, then you should know that number, but it doesn't really have any importance in how we keep track of time. Okay. Now, I want to warn you a couple things about this, though. There's a 4-minute difference in time here, and a lot of people get confused with the concept of the leap day because there's a 4 going on in there, and then there's like a 4 going on in here, but they are completely unrelated things. I will talk about the leap year, I think, in the next lecture, but they are completely unrelated ideas. And another thing that I want you to make sure you don't make a mistake about is not like we just round up the solar day. That would be weird if we did that, because that wouldn't make any sense. We don't round up the sidereal day, and that's how we get the solar day. There just happen to be 2 different numbers, but the number that we care about, the number that we need to keep track of time, is the 24 hours. If we kept track of time with the sidereal day, then what would happen is the rising and setting the sun would be off by 4 minutes every day, and then next thing you know, a month goes by and the sun's coming up at 3 a.m. and that's just chaos. So we don't do that. All right. So now this picture here is my attempt to simplify the celestial sphere. Technically the celestial sphere is this 3-dimensional visualization, which is very hard to get your head around a bit. So what I did is I create a cross section of it. So in this particular view here, imagine your face in the west, and the north is on your right, and the south is on your left. And the arc that you see in the picture here is the meridian. So that's the line that's splitting the sky up into east and west. And so if you just think about that, you can visualize the celestial sphere a bit better. You don't have to think about all the other parts of it. Now, I mentioned before about the relationship with latitude, so I'll say it one more time here. NCP means North Celestial Pole. The location of the North Celestial Pole is your latitude above from the northern horizon. So if we're about 35 degrees north latitude, that's where you're going to find the North Celestial Pole. If we were at a higher latitude, then the North Celestial Pole would be further up in the sky. Likewise with the celestial equator, which is CE here. Remember, that's a line that goes from east to west, but where it crosses the meridian is down from the zenith by an angle that's equal to your latitude. And same thing here. Say we were to go further south, and our latitude therefore goes down. That means that celestial equator would appear to cross further up in the sky. Okay, so you need to know your latitude for these 2 things here, and this is largely why the sky looks different for different observers, because these things are located different places. Okay, so I have some questions here to make sure you understand what we just discussed here. So, which direction would you have to travel in order for the North Celestial Pole to appear closer to the northern horizon? So think about that for a moment. You may want to pause your video. The answer here is south. Okay, so if you walk south, your latitude goes down. Therefore, the angle between the North Celestial Pole and the horizon goes down, and it would appear closer to the horizon. Okay. The way you can think about this as well is if you walk in one direction, the objects in the celestial sphere move the other direction. That's just a relative motion kind of thing. Okay. If we were to walk north, our latitude goes up, and then the North Celestial Pole gets further up in the sky. All right, so we're an observer. We're located in Billings, Montana. There, latitude and longitude are listed here. We want to know what the angle measure would be between the north horizon and the North Celestial Pole. All right, so that is B. Okay, so it's simply your latitude. Billings, Montana is a latitude of 45.8, and so that is the angle, north horizon to North Celestial Pole. Last question here, and this is going to require you to think a bit more because this is not an angle that I specifically talked about before, but now we're talking about what would the angle measure be between south horizon and the celestial equator. So that is a different angle, actually. So you want to think about that for a moment. And the answer here is C. It would be 90 minus 45.8. Okay, so let's go back and visualize that. So what I said was it's the angle between the south horizon and the celestial equator, which, as you can see in the picture here, would be the complement of the latitude. Okay, complement meaning 90 minus. So it's the other part of the 90-degree angle here. And the reason why I mention that is when your latitude is actually very high, these angles are really big, so sometimes it's more useful to talk about, with reference to the southern horizon, because those angles are going to be small. So if you want to do that, then 90 minus is how you would get that number. So that's why that's option C here. Okay, so now what gets interesting is when you start talking about be in other locations. So the picture on the upper right is kind of like Lancaster, right? You see a north celestial pole, and you see where the celestial equator crosses. If you were to go to the equator, and that means that's the bottom left picture here. If you go to the equator, then the latitude is 0. So there is no angle between the north celestial pole and the northern horizon. So the north celestial pole is on the horizon, okay? And the celestial equator would be going through zenith then, because there is no angle there. And so that makes it kind of interesting in terms of how stars rise and set, because when stars rise and set, they follow a line that is parallel to the celestial equator. So that means in this picture here, the stars would rise straight up from east, go directly over your head, and come straight down to west. And that's how things would appear. Since objects move in circles about the north celestial pole, then everything is going to be rising and setting and making big circles along the horizon. If you go to 90 degrees north latitude, okay, so the angle between north celestial pole and the northern horizon would be 90 degrees, and that means it would be directly above your head. So it would be lined up with zenith. And again, since all the stars make circles about the north celestial pole, all the stars are making circles about the zenith. And that creates a very peculiar situation where you don't have anything rising and setting, because everything is just doing giant circles above your head. Even things close to the horizon, they're just doing circles in the sky. Nothing rises, nothing sets. Your horizon and your celestial equator are completely the same. Okay, and so that creates a very different environment. The picture on the bottom right is just a picture of what it would be like in the southern hemisphere. I'm not going to talk about that simply because it's not different in any way than how it is in the north. It's just that the celestial pole would be located in the southern part of the sky and the celestial equator is in the northern part of the sky, but everything else about it would be identical. So, all right, so these pictures here give us a good illustration of how the stars are actually rising and setting. So these would be for like a latitude that is similar to Lancaster. So when we look to the east, the stars rise, and they rise at an angle, and that angle is proportional to your latitude. As we said, if you're on the equator, things go straight up. The further you go north, the more of an angle there is. And if you're really far north, the angle that is made with the horizon is a very shallow angle. And then when you actually get to the North Pole, there is no angle. Everything just kind of goes in giant circles around you. When you look to the south, you can't see the south celestial pole. It's below the horizon, but you still see that arcing that's more prominent when you get closer to the poles. And so when we look to the south, we see stars rise and make these very prominent arcs in the sky as they set. And the closer you are to the southern horizon, the more prominent that appears. When we look to the north, this is what we see. We see the north celestial pole up in the sky, and depending on how close stars are to that location, they can take on a very special kind of behavior, which we call circumpolar. We can describe stars or entire grouping of stars like this. A circumpolar star is a star that happens to be so close to the north celestial pole that it is not able to rise or set because the motion of it never brings it close to the horizon. So you can see in the picture here, if you look at Ursa Major, all of the stars except for one are circumpolar here. There is one that just very briefly gets below the horizon. Now, if you remember that the angle between northern horizon and north celestial pole is your latitude, you can see that you can easily alter the number of circumpolar stars that you see. In this particular picture here, if we were to walk further north, That means our latitude goes up. And if the latitude goes up, that means the North Celestial Pole gets further above the horizon, and then we can get that star that's not currently circumpolar to become circumpolar. Likewise, if we walk further south, we can make less stars circumpolar. And if you actually walk far enough south where you get to the equator, then the North Celestial Pole is on the horizon, and then you don't have any circumpolar stars. The horizon cuts right through the North Celestial Pole, I should say, and every single star would rise and set in exactly 12-hour intervals. Okay, if you walk further north, you get more and more stars become circumpolar, and when you get all the way north, then the North Celestial Pole is directly above your head, and every single star becomes circumpolar. You cannot see the southern hemisphere at all. You can just see northern hemisphere stars, and you can see them at all times. They just do these giant circles about you. Okay. One last thing I want to talk about in this lecture, and we're going to talk about it a couple different times in this class. It's an effect that's called precession. Now, everything I described to you so far is true and accurate over the course of 1 year. However, there is an effect that takes place, which is a combination of a gravitational interaction between the Earth and the Moon and the Earth and the Sun. And at the very bottom of the slide here, there's a YouTube link to a video, and I'll put it in the description so you can watch this. I mean, you only really need to watch the first maybe 3 or so minutes of it, but it kind of illustrates what precession is very nicely. But what it is effectively is this. The Earth's axis of rotation relative to the plane of the solar system has a tilt to it. It's 23.5 degrees. And what happens is precession is an effect that causes that axis of rotation to sort of wobble around. And it wobbles in such a way that the angle does not change, but the direction changes. This is very common when you see like a spinning top. As the top starts to wind down, you start to see the axis rotation do this wobble in effect. Now, over the course of a year, it's not a big deal, but over the course of 26,000 years, there is a complete precessional period that occurs. Now, the reason why I'm mentioning this now is because precession causes the North Celestial Pole, or both poles really, to change direction. Now, it just so happens that right where we live here, at this moment in time, that the North Celestial Pole is extremely close to Polaris. And that is a coincidence. There's no particular reason why there's a star near there. And we know in the past that was not the case. When we look at very ancient historical records from civilizations that really paid attention to the sky, they observed other stars to be pole stars. That star Thuban, you can see in the picture here, back in 3000 BC was seen to be the pole star. And this changes. And Vega, which you see at the top here, that is a star that generally appears directly overhead at night during the summertime. But in 12,000 years or so, enough precession will take place where that will change. And like I said, again, it doesn't affect really much over the course of a human's life, but something that we have noticed when we look back at really ancient historical records, that things have changed. And in fact, this is actually something that needs to be considered when you're using telescopes, really high quality telescopes, because precession, while it's a small effect, high quality telescopes have a lot of precision on them, and the positions of stars in the sky do shift over the course of a year significantly in large telescopes. So this is an effect that professional astronomers really do need to take notice of, actually. But I recommend you watch the video because it illustrates it very nicely. Why it happens is a little bit complicated. You just need to know what the effects are. We will bring this up again because, as you may or may not know, this 23.5 degree tilt in the Earth's axis is what is causing seasons to occur. And if precession is changing the direction of that tilt, then it's going to alter seasons. So when we talk about seasons later on in the class, we will have to mention this again to explain how seasons change over long periods of time. right, so this is the end of the first part of the video for this week. There will be a second video for you to watch, so check that out.